Okay, in this video I do want to go through a couple of examples of how to handle use substitution when we're working with definite integrals. And it might seem like it's a very simple conversion or step beyond what we were just doing in the previous videos, but actually there is a little catch to it. And I do want to show you how I would work with that. So if you notice here we have a function composition where the inside function is x squared plus 1. Its derivative is 2x, which a constant multiple of which shows up on the outside. So we're good to use x squared plus 1 as u here. And du is going to be 2x dx. Again, we only need to match up x dx. And so I'm going to divide both sides by 2. And I'm going to go back to the original function. And recall that x dx is now 1/2 du. And x squared plus 1 is just u. So I'm ready to rewrite this now, only there's something very, very important that I have to pay attention to. So first I'm going to swap out the x dx and write that as 1/2 du. And the 1/2 is a constant, so it comes out. Then I have x squared plus 1 to the third. X squared plus 1 is just u, so I'll write that as u to the third. Now the big mistake that most people would make at this point is just to write in my limits of integration as 0 and 1. However, those limits of integration are really for x equals 0 to x equals 1. They're not for u equals 0 to u equals 1. And so I'm going to note that there, and it's really an important distinction to make. Many students, or some students, like to do this problem this way, which is fine. But then I'll show you the way that I prefer to do it, and I will do it every time from now on. So this integral is no big deal. I can integrate u to the third, that's just u to the fourth over 4 times 1/2. And because I'm doing definite integration now, I'm going to put that into brackets. And I'm just going to note again that I'm working with limits that are written in terms of x and instead of in terms of u. So at this point what I would need to do is swap out my u. And since the 1/4 is also a constant, it can come out. So I'm going to consolidate those. And now when I swap out the u, now I'm in terms of x, and I don't have to worry about stating that my limits are in terms of x, because everything is in terms of x now. So I would simply, so at this point I have 1/8, and I'm going to evaluate the antiderivative at the upper limit minus evaluate the antiderivative at the lower limit. And I get from that 2 to the fourth minus 1. So that's 16 minus 1, which is 15. And that's divided by 8. So my answer is 15/8 here. And the point here is that if you're working with limits that are in terms of x, when you swap out to write the integral in terms of u, and you integrate it, you have to swap back your x's before you apply your limits of integration there. Now I'm going to show you another way that I will always go about doing this type of problem. And so we start with the original problem. Again, we have u is equal to x squared plus 1, du is equal to 2x dx, 1/2 du is equal to x dx. And so I'm going to write 1/2 integral u to the third du is my new integral here. Now what I'm going to do, instead of writing those limits in terms of x, I'm going to do this. I can convert those x limits to u limits. And I'm basically asking the question, what is u when x is equal to 1? Well, I just plug x into the formula for u and I get 2. And I work with my lower limit. What is u when x is equal to 0? Well, u is equal to 1. And we find that by plugging x equals 0 into the formula for u. So now I have two limits that are actually in terms of u, and I can use those. Now when I do it this way, I never need to swap back to x's. Everything is in terms of u, and I can do my integration. And you'll see how much simpler it becomes. So the antiderivative of u to the third is u to the fourth over 4, and I'm going to integrate that from 1 to 2. 2 to the fourth is 16, 1 to the fourth is 1. And I still end up with 15/8. But I think that the calculations were a lot simpler when I did it that way.